Okay, so thank you for joining us. My name is Dmitry Larko, and I'm going to talk about feature engineering and the ways how we can automate this quite complicated process. So, sorry, let me start from introducing myself. I am a Kaggle Grandmaster. I'm currently ranked in the top 100 on Kaggle. Well, I do Kaggle for last 5 years and kind of stuck in this process. So basically, one of the things I learned from Kaggle competition is how important feature engineering might be. The first slide in our presentation was actually about like I was going to find some quotes on the feature engineering, how important it is, and actually I was quite surprised how many famous data scientists actually share the same vision about how important feature engineering might be. So technically speaking, I have to cherry pick the quotes from famous people who actually think, regarding the feature engineering process. And I cherry picked the three guys, like it's Andrew Ng, Pedro Domingos, and Marios Michailidis. I would say these three guys actually define myself as a data scientist. So thank you them for that. And so basically, a lot of people share the same vision. So what distinguishes the good data scientist from the best data scientist and how exactly he engineered his features. And so basically, we can continue. So on this diagram, you see like the common like a machine learning workflow or machine learning pipeline that usually happens in the enterprises. So of course, we start with from data integration, then go to data quality and transformation, and ideally we should get the modeling table, which has the features and the target we would like to predict, and then go and the iterative process of model building, and finally we get the model or models or ensemble of the models as the output of the pipeline. The place of Driverless AI, it's the last three steps basically. So we don't do data integration. That's a very challenging and complicated task by its own. Same for data quality and transformation. So we assume you have a well-prepared data set, or at least some data set to start from. And the goal of this current presentation is just to speak about feature engineering, which happens on the very first step. So basically, we're not considering the fine-tuning of the model and model selection. We just talk about feature engineering and what kind of features can be found before that process. So what is a feature engineering from my point of view? That's a very simple toyish example. What kind of feature engineering, how important feature engineering might be. So as you can see, you have two different classes in 2D spaces and 2D space. And these two classes are not separable using any linear classifier. So you cannot draw a line to separate these two classes. You have to, and basically right now you have two options. You can implement a more complicated model, let's say, for example, a regression tree or random forest. Or you can change the feature so you can actually use a linear model instead. So, and let's say in this particular example, that's really possible. So let's say if you present your points instead of Cartesian coordinates in polar coordinates, these points will be very easy to separable by linear classifier. So using the right features helps you to build up simpler models, or models more stable, or models which be easier to, or you can help your model to approximate easily to the current problem. What is not feature engineering from this point of view? So as I mentioned before, initial data collection cannot be seen as a feature engineering. A target variable and creating of target variable, it's an extremely important step. It's basically defines various steps, but it's not a feature engineering by itself. Feature engineering usually is guided by selected target variable and selected metric and selected, of course, business problem. So duplicates, missing values, mislabeled classes, it's data cleaning, it's a QA. Again, it's a very extremely important step, but it's not a part of feature engineering. Scaling and normalization, that's it's a very common step, especially for neural nets and linear models. But honestly, I don't think it's can be seen as a feature engineering by itself. Feature selection. again, it's a separate problem that can be and should be actually done after all, like all on top of your feature engineering process. But again, it's not the scope of our current presentation. So basically, feature engineering cycle looks pretty much like this. So you have a data set, you try to come with some hypothesis set or like create some hypotheses, you validate them, and of course you apply them. And the process is highly iterative. So as soon as you find some useful features, you have to repeat this process from all these, using the founded features, or let's start from the scratch again. It's up to your behavior. So, and of course, how exactly can you, basically before you can start feature engineering, you have to have some candidates. Let's say some obvious transformation you usually, or some obvious feature engineering you do. And how you can get this set of hypotheses to test, to start from. Well, of course, like domain knowledge, if you have any about this particular problem, that's extremely valuable source of information. Your prior experience, how exactly you handle this type of data and previously, that's again a very valuable source of information. EDA, exploratory data analysis, that's another way to visually go through the data set and to see some feature interactions or get some ideas how you can engineer your features. And of course, machine learning model feedback. For example, you can monitor the weights for linear regressor, or you can check the splits in tree to see how exactly features interact to each other and which feature is actually the most important ones. Hypothesis validation. So as soon as you generate some features, you have to validate them, how good they are, how reliable they are. And that's a very interesting process by itself. Now, of course, you can do it in cross-validation manner. You also have to pick up, so you also have to pick up the right metric. And of course, you also would like to, you need to pick up a right machine learning model you feed with your engineered feature. And of course, because it's a very iterative process, you always have to think about how to avoid leakage, because as soon as you continue to check your hypothesis over the very same validation set, you eventually overfit to this validation set. So you should be very careful in how exactly you're using your validation set and to avoid overfitting. So yeah, and that's one of the reasons why feature engineering is so hard. So basically, it's very time consuming. You have to run 1,000 of experiments. And because people, unfortunately, at least for myself, that's true, I cannot visualize like in my head n-dimensional data sets. It's very hard to come to some with some good feature interaction and feature engineering like on top of my head. So it requires a lot of basically experiments just to try to find the reliable features. Also, well, of course, obviously, if you have domain knowledge, it's always you should always incorporate them into your data set. Again, and some powerful feature transformations like target encoding can introduce leakage to your data. So you should be very careful when applying it in a real life scenario. So again, why feature engineering? Well, it makes your model simpler. Eventually, of course, let's say you can, it's okay if you're not using any feature or any engineered features. You just apply, let's say, XGBoost or GBM model to your raw data. You can get a very good predictions anyway. But in some cases, it can require you to build, let's say, 1,000 trees or thousands of trees to get the same results which you can get just building 100 trees and using more smart features. So basically, the right features and right feature engineering and validation process, that's what defines Kaggle winners from the rest. And the key elements here will be the target transformation, feature encoding, and feature extraction. So of course, it's the naming is quite unstable yet. So, but let's start from that. So by saying target or data transformation, I mean actually in some cases, especially for regression task, it might be a very good idea to transform your variable to make it more normal look, let's say, to make it more close to normal distribution, to a bell curve. So like, for example, log transform or applying like a log base of 2 or 10 will be might be quite beneficial. Or actually even applying a sigmoid function to your target function might make it more normal-like, providing more like a normal distribution look. As one of the examples from one of the Kaggle computation, if you just transform the data set, let's say in this plot, you can see how transforming the target variable impact on the behavior of a different XGBoost models. So on the x-axis, you see IDs of a randomly selected different XGBoost models. And on y-axis, you see the Gini score, basically, the metrical, like the competition metric. And as you can see, if you apply a log 10 transformation, the results become more stable across the different param settings for XGBoost. So most of the algorithms actually, they require you to provide numerical values. Some of them can handle missing values, some of them cannot. Some of them require you to normalize the data. Some of the algorithms can handle the anomalous data easily. But mostly all of them requires you to provide numeric values. So that means you have to somehow encode your categorical features into numeric space, right? And one of the easiest way and one of the simplest way to do it is a so-called labeled encoding. Basically, it's a very straightforward and simple solution. You just map your categorical levels into the integers. Let's say you just sort your categorical alphabetically and apply, for A you apply 0, for B you apply 1, for C you apply 2, and etc. This is the downfall of this approach, that you introduce some sort of order in your data set, in your categories, which is not exactly taking place. It might be okay to do this kind of encoding for gradient boosting methods, because even in that setup, XGBoost or GBM can handle data quite good. But it's unpreferred approach, just because you don't incorporate any domain or previous knowledge to your categories. A wide known approach is one so-called one-hot encoding. So then you just transform your categories into individual binary features, and it's very wide used for linear models, for neural nets, etc. So as I mentioned before, the example of label encoding, so you basically encode the feature A into the zeros, the feature B encoded as ones, and feature C encoded as twos. For one hot encode, you have 3 columns added. So if feature 1 equals A, you have 1. If it's not, it's zeros. If feature 1 equals B, you have 0 for A and 1 for B. So basically, you create a very sparse matrix and very sparse representation. That neural nets and linear models can handle that easily. Tree-based models like random forest or GBM don't appreciate that too much, basically, especially if you have a 100 plus levels in your category feature. In that case, amount of columns becomes too big for random, and these are kind of homogeneous columns, and random tree-based methods like random forest doesn't like this kind of feature encoding. What also you can do, you can encode your features as frequencies. So basically, what I mean by frequency, you just count how many times your feature you encode this category level in the data set, and you just divide this for total amount of rows in your data set you have. So basically, that you can see that as a probability to randomly pick up this particular feature out of the column or this column, basically. And because feature A in this example, you encode a feature A 4 times out of 9, that means you encode it as a 0.44. B is a 3 times out of 9, so it's a 1/3. And C is you encode a C category level just twice, so it will be 0.22 frequency. And probability of meeting this feature in the data set will be 0.22. That's a quite robust approach, again, because you don't introduce any leakage. But let's say, what if you have a balanced category levels in your data set, like yes and no, for example, and they both they both exist like in half of your data set. But in that case, you have a frequency of 0.5, and that means you won't be able to distinguish from them anymore. You have a column with a constant value. So the target encoding is a very, very widely used on Kaggle computations. And basically what you do, you just encode your feature using a mean value of the target variable of your outcome. And this particular case, as you can see for feature A, you see a positive target value 3 times and negative, which is 0, is just 1. So that means there is a 0.75 probability of meeting once in A in this particular categorical level. For example, for C, you always have once. That means you're almost 100% sure you always have once in C if you see the category level C. So a downfall of this approach, that might be if you have a high cardinality feature. So if your feature has a lot of category levels, and some of them actually quite rare, you introduce some sort of a leakage in your data set. So instead of actually create a general pattern, your model will just memorize. Let's say in this example, it's C always produce once. So there is nothing more to learn, basically. It's enough to be able to produce a very reliable outcome, which might be not the case in actual life. So to avoid this kind of overfitting and leakage, you can use leave one out schema. So basically, idea is quite simple. When you're predicting the, let's say for the row which highlighted in green, which has a feature A, you would like to predict the mean outcome using leave one out schema. So you just exclude this particular row and use the rest of the row with A's to calculate the mean outcome. In this case, for green row, it will be just 1 because all others A's always has 1 as an outcome. In blue case, for row in blue, which has a feature B, the leave one out schema will be just 0.5 because the rest available columns have the same amount of ones and zeros, so it's always will be 0.5. That's a very strong regularizer, and it really helps you to avoid the a direct leakage. But also, it might be a very good idea to use some sort of a Bayesian smoothing. And by Bayesian smoothing, I mean a very simple idea here. Instead, replacing each category level with a mean of this level, you actually calculate a weighted average for the mean level, the level of the mean of the level, and the overall mean of across the whole data set. The trick here is how you calculate exactly the weights for these two parts of your equation. So, and basically you have to introduce a function lambda, which actually depends on how many records for this particular level you have in your data set. For example, it can be a sigmoid-like function. So, and here for the blue line, I have an inflection point around I think it's 2. Yeah, it's 2 actually. And the steepness function is quite high. So basically, as soon as we have more than, let's say, 7 examples, we always use the mean of the categorical level. If we have less than 7 examples for this particular categorical level, we use a weighted average. Is this weighted average between mean of the level and mean of the overall data set. So in this particular example, we have overall mean of 0.77, and here how we can actually change our encoding. So basically, again, we help our future model not to rely on the outcome of a particular level. So basically, we're trying to smooth it because sometimes we avoid our model to be 100% sure on the prediction. Like for example, for C level here, even if our leave1 encode make it 1, because we have just 2 rows with the level feature C, we can like, it's not a statistically significant, right? We cannot be 100% rely on this information. So it's with the smoothing, it's down to 0.88. And actually, let me stop here. I would like to run something for you. So basically, I'm going to run Driverless AI on some of the Kaggle dataset. It is 2 signal rentals dataset. And in test level, it's a free level variable we would like to predict. I'm using log loss as our scoring metric. I'm fixing random seed, so results will be repeatable. And yeah, let's keep it working for a while. Oops, sorry. All right, so what else can be done? So that's we just discussed things that can be done to categorical features to transform them into the numerical ones. You also can do some feature encoding with numerical features, although it's not required because usually your algos, they actually expect you to provide the numerical features. Because previously we just discussed the encoding schemas that should be done to categorical features, just because you have to transform them into the numeric space. This kind of encoding quite optional, although it could be extremely beneficial, especially if your numerical features are quite noisy. So for example, you can bin them using quantiles or histograms. And the quantiles, then we have a population of the same size in each bins, and histograms, then the bins are the same size. So it provides for a different bin IDs. And what you can do with the found bins, so basically you can replace your numerical features with a bin statistics of a particular bin, like let's say a mean or median or standard deviation or maximum, minimum, anything you like. Or you can treat the found bin ID as a category level and use any categorical encoding schema we discussed previously. You also can think about doing like a reductional techniques like SAD and PCA on your numerical features. That's extremely helpful if your features share the same nature, of course, or usually share the same nature. Like, for example, if you have a bag of words as your numerical features from text. In that case, applying SVD or any dimensional integration techniques can help you to build a more stable or even a better model. Also, a clustering can be seen as a feature encoding for numerical features. So you just apply a k-means with a specific number of k to identify the k clusters in your data set, and that again can become a new ID, a new categorical feature. Or actually, you can end up splitting up your data set into 3 different, for example, in k different parts, and fit the separate models to each of the parts. Also might be extremely helpful to find in cluster, and instead of replacing with a cluster ID, you actually can calculate distances to cluster centers for each particular row in your data set, and that provides you quite useful information for your feature model. So again, feature interaction. And these are, again, a toy example how feature interaction might be useful. So there is a very simple function you would like to approximate using random forest. Eventually, if you run your random forest for a lot of trees, or in this particular case, the depth of random forest was limited by 4, and I just built 100 trees. Let's say if you don't have any limits on the random forest and you build 1,000 trees, you approximate this curve like very well without actually applying any features. What I would like to show by this example, by providing some founded interaction with features, you can approximate quickly and build like a smoother surface if you compare it to the fact that you don't provide like some of the interactive or some interactions as a new features. In this particular case, I just added as a power of 2 for both variables I have in my data as a new features, and the curve become like R-square score was actually significant, quite better. Wouldn't say significantly because it's a very simple task, but it was some improvements. So the question is, how exactly we're going to find these feature interactions? Well, again, domain knowledge is like a common source of it's like a silver bullet basically for a lot of cases. And unfortunately, for a lot of cases, again, we don't have enough domain knowledge, or actually we would like to acquire some domain knowledge or some insights by analyzing this particular data set. What else can you do? A genetic programming approach usually is extremely helpful to find the mathematical-like feature interactions, like in this case. These tasks can be solved easily with genetic programming. Also, you can encode some of the feature interaction using ML algorithm behavior. For example, if you analyze the tree splits in your favorite GBM algo, or if you just like have a look into your linear regressor weights, you can identify the most important features. And usually, if you're trying to model some interactions between the most important features, you can find very good features as well. So that's immediately got us to another question. So how exactly we model different interactions? Well, again, as I previously, clustering and KNN for numerical features can be seen as some sort of interactions. It's a distance-based interactions, which is usually quite helpful. Also, as we discussed previously, for categorical features, you can use a target encoding for pairs, and basically you take a couple of features, columns in your data set, and treat them as a unique category level, and you encode this unique pairs and you treat these unique pairs as a new categories and any new features, and you encode them using target encoding or any type of encodings we discussed previously. In case if you would like to model interaction between categorical features and numeric, you actually can encode categorical features by different statistics of the numerical features themselves. So basically, for each category level, you just count, let's say, a mean value of a given numeric feature or features. You also can calculate standard deviation or minimum, maximum, or like any metric you would think might be useful. Usually, mean, median, and standard deviation are quite useful. Minimum and maximum are not that informative, but again, it depends on the data set and the problem you're trying to solve. The last high-level topic I would like to mention, that's a feature extraction by itself, because sometimes in your feature you can have hidden features and you would like to extract them manually. One of the easiest examples is a zip code, for example. Zip code is a 5-digit number, but technically speaking, it's I think you can split up into 3 numbers: the first 2 digits, the next 2, and the last one, or the next 3. I don't quite remember. So, but still, it's instead of like having a categorical feature, you can end up with 3. Same goes with the time, for example. If you have a date, you actually can extract the time of the day. You can extract the day of month, day of year, the weekday, and etc., etc. Again, as mentioned before, numbers can be, you can turn, for example, age into ranges. It's up to you how exactly can be done, but there is a lot of features which are hidden inside of existing features. Obviously, if you have unstructured features like textual data, you have to start with some meaningful feature extraction beforehand, because you cannot apply any machine learning technique before you actually munch your data or extract features in some meaningful format. Like a classical approach, which has been here for years. You can do a bag of words representation. You can calculate TF, ADF weights on your words occurrence. You can split the token into subtokens. You can apply n-grams. You can do stemming. You can remove stop words. So basically, it's a classical way how to treat textual data. You also can do like a more fancy stuff using the deep learning approaches, like word-to-vec, or actually, to be honest, for textual data, I don't think word-to-vec is that useful. Doc-to-vec, so when you just represent the whole document into the some vector. That's something that's really needed by business. But the easiest way to do that, actually, let's say if you have and it's kind of work for short descriptions like tweets, for example. You can encode all words in the tweet into into word to vec space and just take an average and treat this average as your document vector. So basically that's it for the presentation. And let me check where we are on the okay. So as you can see, I'm going to show you like a very short presentation what we can do with Driverless AI. And basically, if you're not familiar, on the left lowest corner you see the performance graph, the performance plot, how our model actually perform against the validation set. And because it's log loss, the less the better. We have some improvements already. In the middle, you see a variable importance graph taken from XGBoost in our case. And you can see we not found like a golden feature yet. We just use raw features as our best feature is raw features, which is price. Yeah, I forgot to mention we're trying to predict the interest on the particular ad on particular site. So basically, we're trying to predict how much interest this particular ad will raise on the website. And of course, price is the most significant one, because the cheaper your rent can be, the more attractive this particular post will be. So, and of course, we can see latitude and longitude. The location is one of the most important, as well as the bedrooms. So what I would like to attract your attention to, we'll be able to find some target encoding interactions. For example, you have a building ID and a manager ID. These two IDs actually identify the specific building and specific manager who trying to who posted this advertisement on the website. And it's a categorical variable, so basically we have to encode them somehow, and looks like target encoding of a pair of these features is quite valuable. So we also have some text description, textual features from the description, which was found to be quite good. And what we do, well, currently it's a very straightforward, basically. So what we do with the textual description, we just create a TF-ID of bag of words representation and apply truncated SVD on top of it to perform a dimensionality reduction, basically. So again, that's frequency of address. For this particular data set, display address can be treated as a textual feature, but in this particular case, algorithm chose not to treat it as a textual feature, but as a categorical, and encode it using frequencies. And it turns out to be a quite powerful feature as well. To highlight it's not the overall important score. It's not an absolute score. It's a relative score, basically. Our first feature, the most important features is encoded as 1, and the rest features are encoded as a fraction of the most important feature score. So basically, we see the price is way much important than anything else. Bedrooms are just like a half important as a price. And basically that's all I have for you for today. Thank you for your attention, and we can go to question and answer session.
All right, Dmitry. So we'll go ahead and start with the Q&A. So here's our first question. How do you avoid overfitting?
Yeah, that's a very valid question. Basically, we score our data set. So basically what we do inside of the AutoDL, we apply different transformation to the data, and we score the new found data set on using XGBoost with early stopping criteria, basically. So we're trying to feed XGBoost as good as possible. we do that like over and over again using the same validation data set over and over again, which potentially can introduce us, basically, we potentially can overfit the model. To avoid that, we apply a technique quite similar to reliable holdout technique, which was introduced by Google, I think, a year ago. So basically, we're trying to measure how statistically significant the change in the score is, and depends on that, we decide to show or not to show the new score to the individual, basically. So let's say if the score is not significant yet, I mean not that significant, we return the same score. If it's the change in score is significant, we return the new score. Based on that feedback, we can actually decide which feature transformation is usable and which is not.
Okay, cool. The next question is, how do you decide which features will yield the strongest interaction effect?
So it's basically, there is a two-way how we can decide that, because obviously we don't have and we don't use yet a domain knowledge in the AutoDL and the Driverless AI yet. We're going to, it will be our next steps. So currently we have two sources of information. It's a random search and the feedback from XGBoost, basically, from our tree-based model. So, well, it's mostly like, like explore, exploit problem, basically. And by saying exploit, I see the feedback from XGBoost as exploitation phase. We just take an XGBoost and find and by tracing XGBoost model, we can find the pairs and triplets and four-way interaction between different features. And using our feedback from XGBoost, we can decide which transformation might be the most beneficial for this particular N-way interaction. That's one way. To make sure we don't miss anything, we also just do a random feature interaction search from time to time. That's our exploration phase. At the beginning, we're trying to explore fields like as much as possible. Later, during the amount of epochs, we're trying to switch to exploitation phase more than to exploration phase. Again, the third question. Yeah, that's something I mentioned in my slides. So basically, a question is, are there auto mergers between different data sets? Unfortunately, yeah, I mean, unfortunately, there is none because we don't trying to solve this problem yet. So basically, it's extremely hard problem to solve. Basically, if you like, let's say, given a data table, trying to create the data set using automatic joins and merges, that's extremely wide scope. Actually, it's an ongoing research, so we're not trying to tackle that problem yet. So, does deep learning need feature engineering? Well, that's a kind of philosophical question, because the main idea behind deep learning in the current phase actually is to make feature engineering process automatic, and it works extremely well for unstructured data sets, like for unstructured data like images and text, for example, and sound, of course. So because in that case, you don't have to create the features by yourself. You just use features which neural nets find for you. That's not working in the same way for structured data. So, and technically speaking, we can use a deep learning model, for example, like a MLP in our AutoDL, and create features which is very extremely suitable for it. But I wouldn't say it's like the best approach possible, basically. Still, in structured field, the tree-based methods like XGBoost, LightGBM, GBM, or any other of them provides the best results. And that's our aim. We're trying to find features which suits the best for tree-based, for gradient boosting methods. Does Driverless AI tool separate two types of feature engineering process? One based on target variable and which can be performed after data partition, and one does not involve target variable. Oh, okay. So the question is actually that's an interesting question. So basically, Usually in Kaggle competition, you have two data sets. You have a test data set and train data set. For train, labels are available. For test, you just have the data, you don't have the labels. So, and given that setup, you actually can use so-called semi-supervised technique. So you can use any unsupervised technique on the whole data set. So you just combine test and train together and create your features. And you can use a train set to create the features which actually heavily rely on the target itself. We don't do that in AutoDL. We don't combine train and test just because we're trying to create that in using a real-life scenario. Usually in real life, you don't have a test set available like immediately or at the same time during the training time, basically. So in that case, these kind of supervised approaches might be unapplicable at all. So for Kaggle competition, I would like to try that using our Driverless AI. For real life scenario, no, I don't think it can be done, let's say, for all cases. I like this question actually. So can I send you a data set? I'm very curious. Feature reduction and feature engineering could happen for this particular data set. Yeah, sure. Yes, please do so. Please do so. It would be actually very nice to tackle our Driverless AI against the real life problems. That's I mean yeah, I'm more than welcome you to like send us any data if possible. I would like to try what we've done for. What we've done is our product on a data set, on any given data set. How do you deal with severity in balanced data set? Some things like claims frequency in insurance data or click rate in ad campaign. Honestly, right now we don't have a specific technique for imbalanced data set. That's in our roadmap, basically. And you know, actually, from my experience, to be honest, I still struggling how to automate this process. So basically, a lot of techniques which are available right now a lot of techniques which are available right now are not that applicable for any given problem, I would say. Let's say, you know, like even the common technique, like, hey, you can just upsample your minor class or downsample your major class. Even these techniques can be applied wrongly, like in most of the cases. You have to be very careful how you do that exactly. And so it's an area of research. I'm looking forward to apply some of these techniques like S-mode and upsampling, downsampling to Driverless AI. It's on our roadmap. Right now, we don't do any specific. So let's say if you have a highly unbalanced problem, like ad campaign might be a very good example actually, you have to do upsampling and downsample by yourself before apply a Driverless AI. Later to do automated for you. How important is the choice of the scorer in this example log loss? Extremely important. So basically, you will get a different feature set depending on what kind of scorer you would like to pick up. And the choice of the scorer actually, it's not, let's say, it's a very business-driven decision. In my case, in my humble opinion, it's almost a business-driven decision. So basically, that depends what exactly you're trying to optimize. For example, let's say if you care about the order of your predicted roles, you can pick up AUC, for example, right? Let's say, especially if you would like to make a calls to potential churn customers, you would like to rank them somehow, right? To make sure you call that like the top 100, which like has the highest probability of being churned or of churn in the future. In that case, AUC is like your weapon of choice, or Genie because it's ranking metric as well. In case if you care about some sort of the smoother probabilities, log loss is a good choice. Or you do a multi-classification because AUC can be done for binary classification, but for multi-classification, log loss will be like my weapon of choice. So same goes for regression task. It really depends on the business problem, on a given business problem. For example, if you care very much about the distance between actual predicting and between actual and predicted values, you have to pick up like a mean square error, for example, which penalize the outliers basically. If you don't care about it, mean average error might be okay for you. If you actually care about, if you have a difference between over predicting and under predicting the values, that might be RMSLE, might be your weapon of choice, because you just log transform your actual and predicted values. In that case, over predicting pays much more weight compared to under predicting, and etc. etc. So it's a question of the business, but it's worth to mention that you can potentially have a different features depending on what kind of score you pick up. How are you dealing with the high dimensionality features? As you experimenting all the technique you have presented, are you experimenting? Yeah, I did experiment. I mean, basically, the technique I'm presenting, most of them have been used by myself and my colleagues in Kaggle competition, so they usually prove to be quite useful. High dimensionality features. Well, again, if we talk about categorical, high cardinality categorical features, I explained that in my presentation previously. So basically, we just do a careful using leave one out schema. We do a Bayesian smoothing to avoid overfitting on this high cardinality feature. So basically, the beauty of target encoding, you don't have to create a new columns. You're still presenting your categorical features as a one column basically. That's awesome. But I would like to actually ask myself, based on your question, I can ask myself like a broader question: how we deal with if we have a data set with a high dimensionality data set. That's a very interesting problem, because again that tremendously increase the search space for us, because we have to tackle all features available. We have to try different interaction between them. Again, using the feedback from GBM or XGBoost in that case helps tremendously, because we just identify the top features and we limit ourselves and our search to the top features instead of checking all of them at once. Also, we can apply different neural nets-based transformations, which we have in our roadmap, and which will be implemented like in a month or so. To actually consume like a high dimensionality data set and provide, let's say, a smaller vector representation of the data. How do I get away with the feature engineering? I hear all the time that deep learning algorithms don't need a lot of feature engineering. Do you have any examples for? Yeah, sure. So basically, you're right. Deep learning does not have a lot of feature. I mean, you should avoid feature engineering with deep learning as much as possible, basically. And it works for unstructured data like images, text, and sound. That's why there was a huge breakthrough recently in this particular field of knowledge. But with structured data sets, unfortunately, at this very moment, it's not avoidable to have a feature being engineered, because yeah, you can apply the driverless, and that's how you actually that's right. You can apply driverless, and it can find a lot of features for you. So, but in structured data sets, tree-based methods are still winners in, let's say, 99% of the cases, from my experience again, and from experience with the Kaggle competition. I think I can recall one competition which was a mix of structured and unstructured data, and that was won by neural nets. But the rest of the competition usually won by tree-based methods. And for them, you still need a feature engineer. Again, as I showed in my example in the presentation, you can avoid that. You still can be able to build a very good model, but it might take you more time actually, or more, let's say, more trees to approximate. Compare, let's say, if you found a very good features which can be, which will require, let's say, just a handful of trees to approximate and have the very same score. And basically, that usually means the simpler model are better usually, because the more complex your model, the more fragile it becomes, and that requires you to maintain it more carefully. So that's my point. When will be Driverless AI available for preview, beta preview? I think it's right now available. Yes, you just can go to the website. Let's say, let me try to find it for you. So H2 AI, which one? Yeah, I've been there actually. Oh, nice. Okay, and so yeah, that's, you just sign up for a beta. You don't have to provide your phone number, which is good actually, but you have to provide your first name, last name, email address, job type. We need to learn more about you before you can sign up for beta. That's common. Yeah, that's do you have a roadmap slide? We just okay. So basically, it's the current architecture of the Driverless AI basically, and what I explain you right now, we basically somewhat here in the black box. Also, again, so what I've told you right now, just it's a small piece of the overall picture. We just concentrate on providing good features. You still have to fine-tune your model. You should be able to build an ensemble if you like to. Again, to me, actually, one of the most important parts, it's an interpretation of a model you have or you build, because let's say it's a way to build a bridge between feature found by Driverless AI and your understanding of this feature, basically, because sometimes it could be, extremely, I would say, controversial. Like, the feature found might be meaningless for you from the beginning, but that means you have to analyze it, visualize it, and with help of visualization and analysis to understand why this feature is meaningful in this particular case. Can Driverless AI run just on laptop, or does it require 7? Well, it depends how patient you are, basically, to be honest. So yeah, it can be run on laptop. Actually, I do it like all the time. But in that case, and depending on data size, you have to spend more time, of course, compared to a server environment. But there is no any, especially because you don't have any like multi-GPU on your laptop. Potentially, you can have a multi-CPU on the laptop. So, actually, yeah, I heard that. I think one of the company actually released like a 2 GPU laptop, but it weighs like 16 pounds or something, and it requires like a separate battery to use. But yeah, so technically, ideally you should use a server, because the main goal actually is to reduce amount of time spent by data scientists, finding features. So basically, you can run it overnight and find like some meaningful features for you that will be actually extremely helpful, right, for the next day. How does Driverless AI pipeline load and organize pipelines? So basically, right now, the output of the Driverless AI will be a pipeline which contains the whole transformation needed, and as output of this pipeline, you get the transformation, the data set you can use to model the data. Later, we will be able to provide you the overall pipeline, not just as a data set managing or changing or transforming, but there's a model or set of the models at the beginning. So basically, I see that as a one-stop. Basically, you just provide the raw data as input, and you get the score as an output, basically. And inside of this pipeline can be data transformation step, a single model, ensemble, stacked ensemble, like a n-level ensemble, or whatever complex models you would like to have, basically. That's my vision and understanding where we are heading to.
That's all.
Yeah, that's all. And yeah.
Thank you. That's all we have time for today, I think. Thank you, Dmitry, for the wonderful presentation. I think there's a lot of other questions we couldn't get to. We'll hopefully try to answer them offline. As I mentioned earlier, we'll get you the recording and the slides the next day or two. So there are some upcoming events I wanted to tell you guys about. So we have MLConf coming up on September 15th in Atlanta, and then followed up in November in San Francisco. We have the Startup Conference in New York. That's end of September. We are going to be in Money 2020 in Las Vegas in October. We're also going to be at GDC DC in November, which is on the slide. And then finally, H2O World is coming up. That's
Can I go to Las Vegas, please?
That's in December, yes. Anything for Dmitry, right? So yeah, do check us out, and if you're going to be in any of those cities, come and meet us, talk to us. I would love to show you a demo of Driverless AI, give you a beta if you're interested as well. And then so thanks a lot, everyone, for joining. Thank you. Have a nice day.
Thank you, guys. Bye-bye.